We just reviewed the fact that the fundamental theorem of similarity gave us a way of identifying the lengths of segments between points that have been dilated from the same center by the same scale factor. Today, we are exploring that converse. To do so, we're using this example from the beginning of your packet, section 5. The points P and Q have been dilated by the same scale factor, R, but we don't know what R is. The segments PQ and P prime Q prime are parallel. So as you see in the picture, P prime and P prime Q prime looks like it's moving at the same angle that it would never intersect PQ. The first thing we want to do is determine the scale factor, R. To determine the scale factor, I'm going to use the fact that if P and Q are dilated, I know that the length of the segment between P and Q, and the length of the segment between P prime and Q prime is supposed to be proportional according to the scale factor. So I know that the length of P prime Q prime is supposed to be equal to my scale factor times PQ. Think for a moment. Looking at the picture, do you think the scale factor is greater than 1 or less than 1? If you guessed greater than 1, you're correct, and we are going to see why. Ask yourself and write in the chat, why should it be greater than 1? Exactly. We see that the length of the original segment between the points before dilation is shorter than the length of the segment after dilation. This suggests that our dilation had to magnify the size of distances and segments. So we're looking for a number greater than 1. I am going to replace P prime Q prime's length and the length of PQ in my equation using the values given. We know P prime Q prime is 10 and PQ is supposed to have length 5. I'm going to switch to an annotate tool so that we can use a fun color. So P prime Q prime was 10. And then PQ was supposed to be 5. So I'm going to write that 10 equals R times 5. And now let's go ahead and see if we can find the value of R. Take 10 seconds and solve that equation. Great job. We know that we can divide both sides of this equation by 5. And we get that our R value is 2. So our scale factor is 2. All right, so R equals 2. Take a moment to record those notes before I clear the annotations from the screen. The next thing I want to do is figure out, well, where is the center of dilation? I don't have it marked. Take a moment. Do you have a guess? If you have a guess, type it privately to me in the chat. Let me tell you how I'm going to think this through. When we looked at the fundamental theorem of similarity, do you remember what the picture looked like? We had a point that was our center. We had our points P and Q, and then we dilated them to get our P prime and Q prime. And because we dilated them, we then drew the line segments between. So I'm looking to generate that picture. That suggests to me that I should draw a line between P and P prime and a line between Q and Q prime. Let's do that. I'm going to draw a line between P and P prime and a line between Q and Q prime. Now, I think that point of intersection might be my center. So I have added point A, the point of intersection of our two lines. That's going to be our potential center. I want to check that the lengths are right. So I'm going to use that measure tool. That length is 2.7. Let's now measure the length of the segment from point A to point P prime. And we notice that's 5.3. Now, we did this approximately, but you'll notice if you double a number like 2.7, you should get 5.4. So we're pretty close here. 2.7 times 2 would equal 5.4. And so reading 5.3, this is me not being precise enough with my artwork. Is this the center that would dilate Q to Q prime? I'm going to measure now the distance from Q to A. Measure the distance from Q to A, and that was 4. And now I'm going to measure the distance from Q prime to A. Okay. And there now I'm getting 8.1. So again, we see that with the exception of a little bit of error in my artwork, we do have a doubling of the lengths of the segments. So it certainly looks like this is the scale factor. And that's what the converse of the fundamental theorem of similarity says.